The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Starting today on section 1.3, actually we'll finish that today, and that's about the big problem or the most common problem in scientific computing, solving a linear system. AU equal B, how would you do that? So we will certainly do it for some examples, like our free fixed or our fixed matrices. But I thought I'd just put some comments. Often I make comments that go beyond what specific things we will do in detail. Certainly, the workhorse of, if I'm in MATLAB notation, the workhorse would be backslash. That command is the quick, natural way to get the answer U. And I want to say more about backslash. I won't be able to say all the things it does. There's a lot built into that command. And the MATLAB help desk would give the details of all the different things that backslash actually does. It looks first, can it divide the problem into blocks, into smaller problems? It looks to see if A is symmetric. If it's symmetric, because of course that would cut the work in half, because you know half the matrix from the other half in the symmetric case. It goes hopefully along and eventually gives you the answer. Okay, so I'm going to say more about that, because that's by elimination. The method there is elimination. I just thought I would mention that if I had a large sparse matrix, so I was in sparse MATLAB and used backslash, it would try to reorder the rows. Or it will try to reorder the rows in an optimal way. Now, what would be an optimal way? Just so you have an idea of what. So elimination takes this matrix, right? It's got all its rows, and we'll do examples. So the idea of elimination is that it produces a zero. Let's suppose it accepts the first row as the pivot row. And this 1, 1 entry would be the pivot. And then how does it use the pivot? It subtracts multiples of that pivot row from the other rows in order to get zeros in the first column. So then it has a new matrix it's one size smaller. And then it just continues all the way until it gets to a triangular matrix with all the pivots sitting there on the diagonal. Okay, so that's the idea of elimination, and we'll do small examples. Why would you want to reorder the rows? Two good reasons for reordering the rows. One reason, which MATLAB will always do unless it has some good reason not to, is if that pivot is too small compared to numbers below it, it will pick the largest and reorder to put the largest pivot up there. So you like large pivots. Why do you like large pivots? Because for numerical stability, that gives you small multipliers. If this is the biggest number, then all the multiples that you need, the multiple of that row that you want to subtract from the other rows will be less than 1. The multiple is always the multiplier. So let's remember, the multiplier is the entry to eliminate divided by the pivot. So if that entry to be eliminated is smaller than the pivot, then the multiplier is less than 1 and things stay stable. Okay, so that's a picture of elimination, a sort of first picture. And if it's sparse, that means there's a lot of zeros. And where would we like those zeros to be? Where would we like to find zeros to save time and use to avoid all the steps, to avoid going through every step? If this was already a zero, then we have nothing, then it's there, and we don't need to get it there. The job is already done. We can go forward. And if we have a zero here, then it's already zero in the next one, and we don't have to do, that would be the second pivot row. We don't have to subtract it from this row because a zero is already there. So we like zeros. And sparse matrices have a lot of them, but we only like them if they're in the right place. And what's the right place? It's, roughly speaking, it's the beginning of a row. So we're very happy with we would like to get an ordering that looks like, somehow like this. We would like to get a bunch of zeros in there. Oh, well, I really overdid it. Maybe we can't get that many. But my point is, you see the point that those are at the beginning of the rows. So let's say we can't quite get to that, but maybe something more like that, zeros. So we get some rows starting with zeros, and then we get rows that don't. And which of course, I mean, they were there in the first place. What we've done is move them to the bottom. And the reason for moving them to the bottom is that they don't destroy rows below them. Yeah, I didn't show how that would happen. Suppose I had a number there. Suppose that wasn't a zero, and all these were. Then when I do that elimination, I subtract a multiple of that row from this row. Do you see that those zeros will fill in? So fill in is the bad thing that you're trying to avoid. So in this quick discussion of reordering, you're trying to order the rows so that they start with zeros and for as long as you can, because those zeros will never fill in. Zeros inside a band, yeah, just to make the point again. Suppose I have a long row. Then if I have some zeros here, 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 useless. Because when I go to do elimination on these rows, when I subtract a multiple of that row from that row, that zero will fill in. It didn't help. It's gone. And this and this. So zeros sort of near the diagonal are often going to fill in. It's zeros at the far left that are good. Okay. So that's a discussion of a topic that actually comes into 18086. And so does these third words that I thought I would just write on the board. So this would be topic specializing in how do you solve large systems. And reordering with elimination is one way. And a second approach is, I'll just put these words up here so that you've seen them. Conjugate gradient method, that's a giant success in solving symmetric problems, large symmetric problems. Something called multi-grid is a terrific. Incomplete LU. So those are, people have worked hard on ideas for solving problems so large that this becomes too expensive. But backslash is the natural choice. If you can do it, it's so simple. So let me focus on backslash. So backslash is the key to talk about. Let me see, let's just think, what does backslash do? Suppose I had two equations, two different right-hand sides, B and C, with the same matrix A. Would I solve them? Would I do U equals A backslash B and then separately A backslash C? No. If I had two equations with the same matrix, there's a big saving in, suppose I have two equations, well, can I put it I'll make a matrix. I mean, this is what MATLAB would always do. Put those two right-hand sides into a matrix. Then backslash is happy with that. That backslash command would solve both equations. It would give you the answer then would be, there would be two parts to it. What would be the first column of U then? So do you see what I have now? I have a square matrix A times an unknown U, and I've got two right-hand sides. The point is this often happens. If you're doing, say, a design problem, you might try different designs. So those different designs give you different right-hand sides. And then you have a problem to solve. What's the response to those designs? What are the displacements? What happens? So you want to solve with two right-hand sides. And the point is, you don't want to go through the elimination process on A twice. That's crazy. You see how that elimination process on A hasn't, this what I described here, didn't look at B. I didn't even get to the right-hand side part. I was dealing with the expensive part, which is the matrix A. So we don't want to pay that price twice, and therefore backslash is all set up. So what's the first column of U then? It's A backslash B. And now what's another way to write, a more mathematical way to write A? What's the answer to AU equal B? It's U equal A inverse B, right? That would be that's the answer in the first column, and A inverse C would be the answer in the second column. So it would produce those answers. Backslash will produce the answer to the first equation and the answer to the second equation. Will it do that by finding A inverse? No. No. A inverse, for multiple reasons, we don't often compute. If it's 3 by 3, 4 by 4, then it's not a bad idea to see what A inverse looks like. We'll do that, actually, because it's very enlightening to, if the matrix is small, you can see what's going on. But for a large problem, we don't want A inverse. We want the answer. And backslash goes to the answer. It doesn't get there by computing A inverse. Okay. So our examples will show how. Okay. So I'm giving A inverse a little bad comments, right? Why? So I maybe should finish that sentence, and then you'll see me turn around and compute the darn thing. But why do we not use A inverse? Two reasons. One is it's more expensive. If I have to compute A inverse and multiply by B, that's taking too long. Second reason is A inverse could easily be a full dense matrix, all non-zero, where A itself was like tridiagonal. So if A is tridiagonal, you know, all the numbers we need are there in 3 diagonals. We don't want A inverse. You'll see A inverse is full. So two reasons for not using A inverse. Takes too long in the first place, even in the good case, and often our matrix A is got lots of zeros that are not there in A inverse, so we've wasted time. Okay. Nevertheless, let me say something about A inverse. Okay, on the next board. So I don't know if you ever thought about the inverse matrix. Let me ask you this question. Suppose I use the command A \I. What's that doing? That's putting the identity on the right-hand side. Instead of a single vector B, or instead of 2 vectors B and C, I'm now putting N. That's okay. Backslash will work with that. That's a shorthand for solving. This solves all these equations, it'll get my different answers, U1, U2, it'll get n different answers from the n right-hand sides, the columns of I. That'll be, let me take to be 3, 0, 1, 0, 0, 0, 1. I'll take n to be 3 just so we. Okay, that's the identity. So this solves that equation. A backslash I will output U, and here's the question. What have I got? If you have a matrix A, square matrix, and of course you have to create I as EYE of 3. That I would be, this would be EYE of 3. Cleve-Muller's lousy pun. Okay. So, what would I get? What would I get? The inverse. Yes, I'd get the inverse. I'd get the inverse matrix. A black side. Why is that? Because what matrix solves? What's the solution U to A times something equal I? The solution to this is this equation is A U equal I. The solution to that equation is the inverse matrix. U will be A inverse. So that is a pretty, that's pretty, if I wanted A inverse, that's a good way to do it. Other ways to do it would be INV of A in MATLAB and other ways, but this is about as good as you get. Do you see that you get the inverse matrix that way? And it's worth, it's worth giving some words to this, to that fact. How would I describe this? This is a set of 3 different problems. I would describe 1, 0, 0, that right-hand side, as an impulse. That's an impulse, a delta vector with an impulse in the first component. I'd call that an impulse in the second component. I'd call that an impulse in the third component. So my inputs are 3 impulses, and my outputs are U1, U2, U3. What words might I use? I could call those impulse response. Those, if I were in course 6, I certainly would. These would be impulses. These would be the responses to that impulse from our system. So those are impulse responses. But in linear algebra, the words I would use, U1, U2, U3 are the columns of A inverse, right? That's what we just said. U1, U2, U3. So the columns of, let me write that down. The columns of A inverse are the responses, the U's, the solutions to the impulses to N impulses. And these are the columns of I. Do you see? Nothing I've said so far is deep or anything, but it's just, this is comes up so much that it's nice to have different ways to think about this. And actually, yeah, if I had to solve by hand, if I had to find the inverse by hand, I would use elimination on this system of equations. I would take A and put the identity next to it. I would do elimination a lot. Yeah, actually, I'll put that in one. If I had to find the inverse, I would take this block matrix. Is that the first block matrix we've seen? Block matrices are really, you should just get familiar, when you're getting familiar with matrices, they often come in blocks. So here's a 3 by 3 block, here's a 3 by 3 block, the whole matrix is 3 by 6. I can go through the elimination steps on it. If I really go haywire on elimination and keep going and going and going, all the way until A gets to the identity. So I do elimination, and I get it triangular, then I even clean out up above the pivots, and then I change all the pivots to 1. I can get all the way to the identity if the matrix is invertible. And what do you think will show up in the right half? A inverse. Yeah. So A inverse will show up there. So in 1806, I would go through examples of this computation, just to see A inverse appear. There's no reason for us to go through long examples like that. Maybe one 3x3 would be worth doing, but in the big picture, we're going to use backslash. Questions or discussion? So this is the sort of overall picture about the inverse, and now, well, this is about the inverse. This was about elimination. I've got to take a little time on elimination. No, it's too important. It's sort of straightforward and mechanical, but it's like too important to blow away. So let me remove that and do something, put something better there. Okay. Okay. So now I'm talking about elimination. I'm talking about one equation. I'm back to AU equal B. AU equal B. And notice I'm using the letter A rather than K or one of our special letters, because right now I don't know that that's a special matrix. In a minute, the example I do will be one of our special matrices, of course, and then I'll use its letter. Okay. Just a word, though. I thought I would take, now you're getting a lot of big picture here for a minute, and then we'll get into the details. I thought I would just, like this as an occasion to look ahead, to say a word about the big picture of linear algebra. It's got 4 major problems, linear algebra. And there are 4 commands to solve those problems. And those commands, why not know? So those commands are LU. I'm speaking about MATLAB notation, but Octave, Scilab, Python, R, all other would have those, would do these same things. So LU is the command that produces this, but I didn't say what that is yet. Whew. Okay, so that's my job, right? What does this mean? This is real. What's up there? So, okay, to nobody's surprise, MATLAB thought, okay, LU is a good letter for that. Okay. And what did MATLAB think of as a good letter for the command that does this? QR. So if I did LU of A or QR of A, I would get, so QR, I mean, this is sometimes associated with the names of Graham-Schmidt. It makes vectors orthogonal. Let's not to worry about this stuff. You can like close your eyes for a moment here. LU is the first command, and that's what today's about. QR is the key command for least squares problems, maybe the biggest application of rectangular matrices. I'm sure that's the big. Eigenvalues, do you know about eigenvalues? Well, we'll just name the command eig of A. And the singular value decomposition, which you may never have heard of, but you will, is SVD of A. Okay. Can I leave that? It's in the videotape now. And my point is that when we've spoken about those 4, we really have got numerical linear algebra and a lot of pure linear algebra explained. These are the 4 big ones. And I guess what I'm saying is the 4 big problems of linear algebra turn out the good way to describe the answer is as a factorization of the matrix. This is a factor. So now let me say what this one is. I start with a matrix, and I'm going to, what elimination is really doing, if you look to see what is it doing, it's producing a lower triangular times an upper triangular. Let's go directly to that. Let me go directly to that. Let me take an example. Okay. So here's my matrix. Well, I don't have to call it A because you recognize it. 2. Okay. So what's our name for that matrix? T, because the top boundary condition is free. Oh, that reminds me. Some good comments after class Friday brought out something that I sloughed over, that the free fixed matrix, the free fixed problem, is usually one unknown larger than the fixed fixed. Because you remember the fixed problem had both ends fixed. They were not unknowns. The only unknowns were 1, 2, 3 to n in the middle. But people noticed when I was talking about the free boundary condition that U0 came into it, and U0 is not known. So really, the free boundary condition has an extra unknown, an extra row and column in the matrix, and that's correct. We'll see later that in Fourier transforms, cosine matrices are one size bigger than sine matrices. The cosine matrices are free, and the sine matrices are fixed. And now here we're at free fixed. Okay, I want to do elimination on that matrix. And while I'm at it, we'll find the inverse. Okay, but let's do elimination. Okay, just on that matrix. Okay, just to see what this L and U stuff is. Okay, what do we do? The first pivot is 1. It's fine. We're not going to worry about that. Okay, we'll use it now. So how do I use it? I use a pivot. Now here, listen, because here's a convention here. I'm going to use the word subtract. You would say, add that row to that row, right? Because you want to get a 0 here. Forgive me for making it sound harder. I'm going to say subtract, because I like subtraction. Subtract -1 of that row. My multiplier is -1 here. I'm going to say subtract -1 of that row from that. Same thing. You will say, okay, no problem. Let's just do it. Okay, so there's the pivot row. And now when shall I just add? When I add that to that, or as my superego is saying, subtract -1 of that from that. What do I get? I get the 0, the 1, and the -1, right? And then what do I get? So let's just put these these multipliers, the L21. That's the multiplier. 2, 1 refers to row 2, column 1. And this step got the 0 in row 2, column 1. And what was the multiplier that did it? It's the number that I multiplied row 1 by and subtracted from row 2, so it was -1. What's L31? What's the multiplier that produces a 0 in the row 3, column 1 position? It's 0. I take 0 of this row away from this row because it's 0 already. So I'm not going to change. That row won't change. And L31 was 0. Okay. Now I know the next pivot. I'm ready to use it. I want to get a 0 below it because I'm aiming at this upper triangular U. And what's the multiplier now? And what's its number? What's the multiplier number? 3, 2. because I'm trying to fix row 3, column 2. And what do I multiply this by and subtract from this to make it 0? It's negative 1 again. Negative 1. Right, it's negative 1. Sorry about that. Okay. Right. And now what happens when I do that? Can I just do it in place here? Forgive me if I just add that to that. Okay, and I'll get 0 and 1. Okay. And now what do I learn? What do I know at this point? What have I learned? The most important thing I've learned is the matrix is invertible, because the pivots 1, 1, and 1, well, they're all here on the diagonal. This is my matrix U. That's my upper triangular matrix. And yeah, of course.
You said that you were multiplying the first row, times minus 1, and subtracting the second.
I was.
So if you look at the second entry, would that be 1 minus 2?
I'm subtracting from this, so I've got the 2 is there.
From that.
Yeah, that's right. So the 2 is sitting there, and I'm subtracting minus 1 of that row from it, and that would mean taking, yeah, right. That would mean I'm subtracting 1 from the 2 and getting the 1. Yeah. So the row, the typical entry is, the typical result is the row you have minus L times the pivot row. The row you have minus the multiplier times the pivot row. That's the operation that elimination lives on. That's the, elimination does that all the time. Yeah, it's one of the basic linear algebra subroutines, BLAS. Yeah. Okay, now what, this is my U. So that's the goal of elimination, get it upper triangular. And the reason is you can solve upper triangular systems really fast. These multipliers, L, L21 and so on, they go into the L matrix. Now, let me just say it here, that in a way, that example is too beautiful. Seldom am I sorry to see an example come out beautifully. But why do I say this is too beautiful? It's not typical. If I had other numbers here, I would get to other numbers here, and what would be the difference typically? The pivots wouldn't be all ones. That's what's too beautiful here. But let's go with it. I mean, it was worth it because everything came out simple. But the pivots for another problem. Let me just do a second problem here. I'll do the fixed guy. Okay, so let's just do elimination on that. That's the first pivot. Subtract. Now, what's the multiplier now? You're not as quick as MATLAB. MATLAB's ahead of you. So the multiplier is negative a half. Negative a half. So the multiplier is L21 is negative a half. L31 will again be 0. And let's use it so it knocks that guy out. And what did that number come out to be? Do you remember? That was 3/2. I think we looked at that once. And that would be all the same. And then the next multiplier, L32, will be negative 2/3, because when I multiply that by 2/3, it gives me the -1, and then I subtract, and it kills this, and I get 4/3. I just did that quickly. And my main point was the pivots are on the diagonal. They're not all ones now. So this is a more typical one. This is again our U. And our L matrix will be, that's the point. That these L's, these multipliers, fit right into a lower triangular matrix. All these multipliers, and we'll put ones on the diagonal of that guy. And these lower triangular ones will fit in just right perfectly in there. Over here, the L would be, let me construct the L, ones on the diagonal, representing the pivot rows that stayed put, and -1, 0, and -1 as the multipliers so this was L, the multipliers that we used. Okay. One more. We're doing lots of good stuff here, and it's not deep, but it's, how would, suppose the matrix had been singular. We have to realize, okay, this elimination method is great, but it can break down, and it's going to break down. It has to break down somehow if the matrix is singular. Now, what's our example of a singular matrix here? The matrix, this is free fixed, and that by fixing one support, it wasn't singular, but if I want to make it singular, what will I take? Free matrix will have a, so can I, if I had thought to bring color chalk, I'll just erase for a moment for the bad case. The bad case would be free, and how would it show up as bad in elimination? How does a singular matrix reveal itself as elimination goes forward? Because you can't tell at the beginning. What would have gone wrong? We would have had a 0 there. We had a 2 that dropped to 1. But if we start with a 1, it'll drop to 0. That would have been a 0 there. The matrix would have had not have had 3 pivots. This upper triangular matrix is singular, no good. And that tells us back there that the original matrix is singular, no good. So if I can't get to 3 pivots somehow, the matrix will be singular. And that's an example that is. So, yeah. So, and MATLAB would immediately tell us, of course. Okay, so let's go back to the good case for the main point. The good case for the main point. So the good case was 3 pivots. In fact, it was extra good because they all turned out to be 1s. Now, now we're ready for LU. Here's the magic, and I'm not giving a proof. The magic is that the result U, if I multiply the multiplier matrix L times the result U, I'll bring back A. I'll bring back A. So let me just see. If I multiply L by U, so this is now L times U, maybe you can see that I get A. So what is U? Oh, I just have to copy it. 1, 1, 1, minus 1, minus 1, 0. That's, I could fill in the zeros, but I know they're there. That's L times U. And sure enough, if I do the multiplication, how would you do that multiplication? I would say this is 1 of the first row. When I see that 1, 0, 0 multiplying these, I'd say get 1 of the first row. That's correct in A. Here I would say this is minus 1 of the first row plus 1 of the second row. And sure enough, it's the right part of A. And this is minus 1 of the second row plus 1 of the third row. And sure enough, it's the right third row of A. I get A. And that's what, when elimination goes through with no 0 pivots, no problems, just a bunch of multipliers, then that wonderful description of it, A equal LU, is correct. I don't know how many that's new to. I should maybe have thought ahead. How many have seen like L times U before, just to give me an idea? Quite a few. Okay. So it's terrific. Okay. What do I, here I would get L times U. Now this is like a little more interesting because the pivots were not 1s. So that's my matrix U. And here's my matrix L, right? Now, okay, big point. Because we're so interested in symmetric matrices, and this one in particular, or that one, symmetric matrices are good. Now, I'm unhappy about one aspect. So now there's just one part of this. This was great. We got 3 non-zero pivots. We got to U. We got the multiplier matrix, all fine. And we would be ready for the right-hand side, and we would be ready for 2 right-hand sides. We would be ready for all 3 right-hand sides, whatever. But I have one criticism. The matrix A, which was our K, this was really K, was symmetric. That was the very first thing you did. You told me on the very first day. And now it's equal to L times U, but what's happened? The symmetry is lost. Somehow, the L has 1s on the diagonal. The U, as we have it, has pivots on the diagonal. Now the pivots are not all 1s. So you see, the symmetry of the problem got lost. And that shouldn't happen. And there ought to be a way to get back to it. Okay. And now I want to describe the way to get back to symmetry. So LU doesn't keep the symmetry. L has 1s, U has pivots, different. But a very simple idea will bring back the symmetry. And that is peel off the pivots into a diagonal matrix. In other words, there's a matrix, I'll call it D. The D for diagonal. I'll divide those numbers out of each row, and yeah, can I just do that? So I'm gonna write this U as a product of this diagonal D, where I'm dividing the 2 out. So when I divide the 2 out from that row, I'm left with 1 minus a half, 0. And when I divide 3 halves, the pivot, then it makes that pivot into a 1. And what does it produce for that guy? When I divide 3 halves, when I divide that minus 1 by 3 halves, what do I get? I get negative. Division will be 2/3, so I'll get a negative 2/3. And now on the last row, I'm dividing that row by 4/3. When I divide that row by 4/3, what row do I get here? 0, 0, 1. Because I've made the pivots 1. Well, they're not pivots. What I've done is separate out the pivots. So I've made the diagonal 1s just by separating it out. And what's happened? My goal was to get back some symmetry that was there at the start now. So I have a pivot matrix D, and what's that matrix? You could say, well, it's the rest. But that's not what I'm looking for. What is it? It's the, can everybody have a look at it? Oh, I can't raise it. If you look at what we got there, what is it? What's the right name to give it? L transpose, exactly. That's the right name. L transpose. So what am I concluding then? I'm concluding that, let's see, where shall I put this? And it'll come back to it here. Well, here we had, just to show it wasn't an accident, here we had L transpose, and what was the pivot matrix in this too beautiful case? It was the identity. So we didn't notice it. So can I squeeze in the identity? That's the pivot matrix there. But again, we had L times L transpose. The beauty was there, the symmetry was there, and now what's the usual thing? So really, I'm completing this to one more thought. In the case when A is symmetric, I have the L, I'm factoring out the D, and what's left is L transpose. I hope you like LD, L transpose. Seeing the matrix, a matrix on one side and the transpose on the other side, The matrix L at the left and L transpose at the right is just right. So the point of symmetric case we have, and I'll use the letter K rather than A, because now we're getting the matrix is more special. It's that K, or it's this T, or it's any other symmetric matrix. The elimination leads to uses multipliers L, and if I factor out the pivot matrix, then the other part is L transpose. We've seen that just by example, by two examples. Now I want to just look at that, because this is that describes not only the result of elimination, which is the key operation, but it also keeps the symmetry. In fact, the matrix, every matrix of that sort is symmetric. Now, yeah, that's important. Can we? This is sure to be symmetric. We will often see matrices multiplied by their transpose. And I guess so what I'm saying is that if you gave me any matrix L, any diagonal matrix D, and then the transpose of L, if I multiplied those out, I would get a symmetric matrix. And going the other way, if I started with a symmetric matrix and I did elimination and got an L, then the D factoring out would leave me L transpose. So what you've seen by example is what will happen all the time. Now, why is that matrix symmetric? Here we get a chance to show the power of matrix notation, really. I just think that if I have any matrix L, in this case it happened to be lower triangular, but if I have any matrix L, and I have a nice symmetric diagonal guy in the middle, and I have the transpose of this matrix on the other side, I think the result is a symmetric matrix when I multiply. So it's these symmetric factorizations that we're getting to in our important problems, because our important problems are symmetric. Okay, why is that sure to be symmetric? Could you, suppose I asked you as an exercise, prove that L times a diagonal times L transpose is always a symmetric matrix. How could you do that? How could you do that? You could certainly create an example that did it and check it out, multiply, it would work. But we want to see that this is going to be true always. Okay, so how would you do that? I guess, let me get started. I would take its transpose. If I want to show something symmetric, I transpose it and see if I get the same matrix again. So let me take the transpose of this. So I'm answering why is it sure to be symmetric. So let me take K transpose. So this is the transpose of, I have K equals something times something times something, A times B times C, you could say. If I transpose a matrix, how can I create that K transpose out of the transposes of A, B, and C? Do you remember what happens? You reverse the order. It's like inverses. Transposes and inverses both have that key rule. When you have a product and you invert it, they come in the opposite order. When you transpose it, they come in the opposite order. So let me put these separate transposes in the opposite order. So there, I've used the most important fact there, which is just a fact of just a fact about transposing a product. Okay, what have I got now? What's L transpose transpose? It's L. Great. What's L transpose L transpose? Nothing but L. Transpose twice and I'm back to L. What about D transpose? Same as D, because D was symmetric, in fact, diagonal. So what have I learned? The proof is done. K, I've got K back again. This was the original K. So I've learned that K transpose is K. So you're going to see time after time, let me just put these things there. You're going to see an A transpose times an A. That's a most highly important multiplication. Take a matrix, maybe rectangular, multiply by A transpose. So this matrix is certainly square, because A could be M by N, and then A transpose would be N by M, and the result would be N by N. So it's certainly square, but now what's the new property we now know? It's symmetric. It's symmetric, because if I transpose it, the transpose of A will go on this side, the double transpose will go on this side, but the double transpose is A again. So symmetric. Okay. Okay. So I'm plugging away here on symmetric matrices because they're just, what does symmetry mean can I just come back to this idea of responses? Yeah. And by the way, if this was symmetric, would its inverse be symmetric? The answer is yes. If a matrix is symmetric, its inverse is symmetric. These symmetric matrices are a fantastic family of. So I could add that to this. K inverse will also symmetric, without having yet said why. But maybe in words, I'll just say a few words here at the end. I spoke about the response. So what's a typical entry? Say the 2-1 entry, just to carry on with this language one more moment. This is A inverse here. Okay. Now the 2-1 entry in the inverse is an impulse is in the first mass, whatever, gets an impulse. And that is the response of the second mass, the response in position 2 to the impulse in position 1. Now my matrix is symmetric. I'm thinking about symmetric matrices here. So what about here? Here, if I take the impulse in position 2 and look at the response in position 1, so do you see the difference? In general, those could be different. This is the response at position 2 to an impulse at 1. This is the response at 1 to an impulse at 2. You see that I'm multiplying those columns and getting these columns. And what's the point about symmetry? Those are the same. Symmetry is expressing this physical meaning that the response at I to an impulse at J is the same as the response at J to an impulse at I. That's such an important property you want to notice it, and it goes into symmetry. So many problems will be symmetric, and then some won't. We have to admit this won't cover everything, but it covers such an important and beautiful part. So that's today's lecture on LU, elimination, solving linear systems, and then let's move forward to understanding the actual inverses.